So now that we've learned the absolute trick and the square trick and how they're used in linear regression, we still want to have some intuition on how these things get figured out. These tricks still seem a little too magical, and we'd like to find their origin. So let's do this in a much more formal way. Let's say we have our points, and our plan is to develop an algorithm which will find the line that best fits this set of points. And the algorithm works like this. First, it will draw a random line and it will calculate the error. The error is some measure of how far the points are from the line. In this drawing, it looks like it's the sum of these distances, but it could be any measure that tells us how far we are from the points. Now we're going to move the line around and see if we can decrease this error. We move in this direction and we see that the error kind of increases, so that's not the way to go. So we move in the other direction and see that the error decreased. So we pick this one and stay there. Now we repeat the process many times over and over, every time descending the error a bit, until we get to the perfect line. So to minimize this error, we're going to use something called gradient descent. So let me talk a bit about gradient descent. The way it works is we're standing here on top of a mountain. This is called Mount Rainier, as it measures how big our error is. And we want to descend from this mountain. In order to descend from this mountain, we need to minimize our height. And on the left, we have a problem of fitting the line to the data, which we can do by minimizing the error, or the distance from the line to the points. So descending from the mountain is equivalent to getting the line closer to the points. Now, if we wanted to descend from the mountain, we would look at the directions where we can walk down and find the one that makes us descend the most. And let's say this is the direction, so we descend a bit in this direction. This is equivalent to getting the line a little bit closer to the points. So now our height is smaller because we're closer to the points, since our distance to them is smaller. And again, we look at what makes us descend the most from the mountain, and let's say we get here. Now we're at a point where we've descended from the mountain, and on the right, we've found a line that is very close to our points. Thus, we've solved our problem. And that is gradient descent. In a more mathematical way, what happens is the following. We have a plot, and here's a plot in 2 dimensions, although in reality, the plot will be in higher dimensions. We have our weights on the x-axis and our error on the y-axis. And we have an error function that looks like this. We're standing over here, and the way to descend is to actually take the derivative or gradient of the error function with respect to the weights. This gradient is going to point to a direction where the function increases the most. Therefore, the negative of this gradient is going to point down in the direction where the function decreases the most. So what we do is we take a step in the direction of the negative of that gradient. This means we're taking our weights wi and changing them to wi minus the derivative of the error with respect to wi. In real life, we'll be multiplying this derivative by the learning rate since we want to make small steps. This means the error function is decreasing and we're closer to the minimum. If we do this several times, we get to either a minimum or a pretty good value where the error is small. Once we get to that point, then we've reached a pretty good solution for our linear regression problem. And that's what gradient descent is all about.